he approaches the theory of everything top down, or rather outside in, you might say, whereas usually you have the set of accomplished theories, or accomplished in air quotes, and you're trying to generalize them or unite them or both, right? And you're trying to get inside out, right? Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. Today I wish to talk about the procedural theoretical physics of Stephen Wolfram. I'm not gonna talk who Stephen Wolfram is, I'm just gonna state you his theory. Like, if you wish, you can read his details, like the details of his bio or whatever yourself. He's just a theoretical physicist. In my eyes, anyways. Like, I know a fellow when I see one, okay? So, to proceed with that, let's ask a couple of questions to ourselves, like how physics works, how theories work in the first place. Well, I would claim that any physical theory, and I'm using physics as kind of a straw man for any sort of science, you know, because, well, physics have been recognized at some point, at least in history, as the most recognizable science, as the most successful of sciences, at the beginning of 20th century at the very least, and so we shall still think that we're kind of there, okay, even though we're not. But anyway, so how physics works? Well, it has certain approximations for the reality, whatever it is, how Stephen Hawking loved to say. By the way, watch my video about Stephen Hawking in the description. So we have some approximation of the reality, which we describe with the help of mathematics, right? In a mathematical language, and we try to tell a story about reality, again, told in mathematical language. And see my video, Nature of Knowledge, I'm going to reference it many times in this video, where I claim that any knowledge is just a bunch of stories we tell each other about the world, alright? So models are systems based on very few concepts. So we introduce certain concepts, and we tell a story about them. That's what physics is about. It's just that if you tell this story in the language of mathematics, you get a physical theory, essentially. So we tell stories with these actors, for example, electron, point-like particle of electron, or electromagnetic field, or strong interaction, or gravity, etc., etc. Then we arrive at certain, like, amounts of stories. We try to generalize them to, like, produce a physical law, right? So it's a story that's a mother to many small stories, right? And then we try to unite neighboring mothers of stories, you know. We try to unite electromagnetism with weak interaction. We get electroweak theory, you know. The Salam and, what's his last name? Goddamn. Weinberg, Salam, right, etc., etc. Yeah, but then we see that, well, not all such unifications are possible, right? So the so-called theory of everything is a bit of a tough nut to crack. So, for example, we cannot really unite quantum mechanics with relativity, because they use incompatible language in the first place. Incompatible language in terms of telling their stories, their main stories. Like, again, watch my lecture on quantum mechanics, link in the description. And I promise you, sometime later, I'll give you another lecture on Bohmian mechanics, which I think is much better than vanilla quantum mechanics. But vanilla quantum mechanics, you can find it in my lecture, for a layman, so you don't have to be a student or anything. Yeah, so, returning to the issue of incompatibility of QM, quantum mechanics, and relativity. So in relativity, its vocabulary is based around space and time, right? Or space-time, if you wish. Whereas in quantum mechanics, for example, space doesn't even exist in the first place, and time is just a free parameter. So it doesn't care about neither space or time, strictly speaking. Whereas relativity cares only about space and time. So that's why you cannot translate stories from one to the other, or vice versa, right? That's why you can't really unite these theories, because the stories they tell are incompatible. They're just intranslatable, you know. I can't give you any other example of this sort, but anyways, hopefully you get the idea. Again, watch my lecture on quantum mechanics. So, returning to Stephen Wolfram, what's his contribution to this thing? Well, Wolfram asks. He actually doesn't. This is this is my interpretation of his theory, or his approach, rather, if you wish. Yeah, this is how I would advertise his theory, if you wish. Okay. So Wolfram asks, what kind of stories can we tell in principle, like in general? A priori, you might say, or a priori in Latin, right? And I've deliberately chosen this formulation because it reminds you of what? Of Immanuel Kant, right? Kantian approach, which was a huge revolution in European philosophy. It has given birth to German classical idealism, so-called, or German classical philosophy in general. And by the way, let me tell you a little anecdote because it's appropriate. It's actually not, but anyway. So Nietzsche have made fun of Kant for this when he became disillusioned by, again, German classical philosophy. So Nietzsche claims that the Kant's main question was, how are a priori synthetic statements possible? Nietzsche's claim, again, is that Kant answered to this is that, well, it's just because we are able to make them, these statements, right? And Nietzsche, again, gives an example from Molière, you know, the French playwright, is that the word? From Imaginary Invalid, the piece of Molière, where he says that opium gets you to sleep because it has the power of getting people to sleep, right? So the question is how we can make synthetic a priori judgments, and Nietzsche says, well, I mean, it's all what Nietzsche said. Well, okay, never mind. Kant asks, how can we have synthetic a priori judgments? And the answer is because we can, right? So this is the same thing that Molière has in his piece. So yeah, returning to Wolfram, okay? So the Kantian revolution in theoretical physics, as I would call it, actually. Wolfram doesn't call it that. So Wolfram wouldn't formulate it as I do, as I've said. So, yet I still claim that he kind of does to theoretical physics what Kant does to philosophy. So he's asking, what theories are possible to construct for us? Instead of more mundane questions of like, which theories are real or you know, true, or which theories we can unite with each other, etc., etc. So yeah, and again, already constructed theories, that's what I'm talking about. So Wolfram offers us, if you wish, a top-down approach, an approach from outside, if you wish, versus the usual approach, and by approach I mean approach to theory of everything. So Wolfram offers us the approach to theory of everything from the outside, kind of homing in onto it, whereas the usual approach towards the theory of everything was from the inside, like, we know this works, so let's try to grow it, you know, let's try to unite it with some neighboring pieces, right? So we kind of grow it from the inside out. So that's kind of the difference I'm talking about. So by definition, the most general theory we can construct is a subset of all the theories we can construct. I mean, it's obvious, right? From the definition thereof. I mean, from the way it's formulated even. So Wolfram says, well, let's take a look at what theories we can even construct. And then the ultimate theory, like the most general theory, would be contained in this. Rather than we say we have this theory that kind of works and this theory that kind of works, let's try to expand it to the most general theory. Wolfram says, well, no, let's think about what can we construct at all as human beings, and then narrow it down to the most general thing we can construct. Hopefully you can see the difference, right? So yeah. And remember, actually, my definition of objectivity that I've given, again, in the video, actually, down there, in the description, Nature of Knowledge, where I've said that anything that can be communicated is objective, okay? So this is kind of the approach that Wolfram takes here, even though he doesn't know about it. So yeah. Actually, speaking about objectivity versus subjectivity, I really like, and I've mentioned this in one of my previous videos, I don't remember which one it was, but I've specifically advertised this video there, and I've said that I'm gonna make a video about Wolfram, where I've said that physics is subjective, right? Science is subjective in the sense, at least in the sense that it's made by humans and for humans. And I really like I've watched many interviews of Wolfram recently, and he uses this phrase, observers like us, and he specifically means us means humans, and I really like it. Like I get the deal. Like he talks about we have this science, exactly this kind of science, because we are humans, and this is a huge achievement, just as I've claimed in that previous video, whatever it was. I don't even remember. And this is kind of the thing I talked about in my own video, Onion of Aliens, whatever part it was, 1, 2, or 3, because they're all out there. I'm gonna link them in the description as well. So yeah. Okay, so we have the Kantian approach to theory of everything. We're moving from the outside, we're trying to delineate this space where the theory of everything can reside. How do we do that? Well, again, watch my video on Nature of Knowledge. How do we tell any story? How do we get any knowledge? We have to have a set of actors who do something, right? There's also a narrator, but in science it's always random human being, observer like us, as Wolfram says, right? So we have a set of actors. In Wolfram's approach, it's basically some elements. Let's just give it this anonymous name. And they act in some sort of deterministic manner. This is what they do, right? We have the actors and what they do to tell the story. But we have certain rules of what they do. So they don't just do whatever they want, they behave according to certain rules. And this is, I think, a little bit problematic. It's the problem of causality, you might say. So causality is essentially a basis of science. So, for example, Big Bang Theory is not a theory because it's not scientific, because it doesn't have causality, like all the laws of conservation are removed, etc., etc. But nevertheless, so my big question to myself in this section is, can causality exist without determinism? And it's a good question, and I'm not really ready to answer it at this point. So let's just assume that causality requires full determinism, alright? But I'm not convinced it does yet. I have to think about it, to be honest. So anyways, let's just assume it does, okay? So we have full determinism. So we have a set of elements, right, which behave in a completely causal, deterministic, rather, manner, okay? So if you have a black box of this element, you put one signal into it, it gets one output. You get the same signal into it, it gets the same output, okay? So no free will, no indeterminism in between. That's the most important part, probably. So what Wolfram then notes, and it's a very even more important part, arguably, is that even simple systems with very simple rules, so even very simple sets of elements with very simple interactions between them, can behave in incredibly complex ways. So it's sometimes, if not almost always, that sounds silly, but well, okay, a lot of times it's impossible to predict which patterns they would form from first principles, which basically means that whatever I've said to you above, when I've said that, well, usually in physics we have approximations, so we say, well, we have this big lump of matter that looks like a simple mathematical object, right? So this is out of the box right now, like in outer space, okay? So we get rid of that. So yeah. So this is what Wolfram himself calls computational irreducibility, which means that, again, I think I've mentioned this already, but anyways. So approximations are impossible, and this is one of the key topics of his book, New Kind of Science, which was published in 2002. So yeah, it means that we cannot simply, well, what does computational irreducibility means? Irreducibility means we cannot reduce the actual problem, the actual set of elements, to some simplistic picture, right? We cannot say that a bunch of atoms that make up a ball behaves like a ball, you know? We have to actually look at the atoms themselves. This is kind of, in a very simplified manner, what it means. So yeah, so generally, we shouldn't assume that such approximations or simplifications are possible, because at least in some cases they're not. So generally we cannot assume they can, because again, see above, we're trying to go from outside in, we're trying to limit the space of possibilities from outside, so to speak, from top down, right? So which means that if there are outliers to simple theories, we should get rid of simple theories. We should always keep in mind the outliers, right? So if some simple systems with simple set of rules disbehave, so to speak, we should assume that all the systems would disbehave. And that's what the computational irreducibility is about, essentially. So yeah. So no large concepts like a ball of particles are possible, because a ball of particles is at least a bunch of particles. So it's not a ball anymore, if you wish, because these simplifications are overly simplifying, if you wish, etc., etc. So we need sort of smaller and more anonymous blocks, anonymous elements, and almost like propertyless elements, again, if you wish. Well, again, except for the simple rules. The simple rules should be simple rules. And again, the best illustration for the elements plus simple rules would be given by Wolfram himself. Maybe I'll give you some pictures on the screen right now. Maybe, I don't know, maybe I should put my hand lower, whatever. So, it's the so-called cellular automatons, right? For example, the ones that color the next cell to themselves with a different color depending on X, Y, and Z, you know, whatever set of rules. But they should be simple. That's kind of the thing. Okay, so the problem with computational irreducibility is that you always, and then again, always, we assume that it's always irreducible. So you always have to go out there, you know, and actually make the computation. Because even for a simple set of elements with simple rules, you sometimes get unpredictable results, which means, well, since it's unpredictable, by definition, you have to go on and make the calculation to see the result. because it's unpredictable otherwise. This is computational irreducibility in a nutshell. So causality in this sense, even though it's there microscopically, it still becomes non-trivial and, well, almost absent, you might say, macroscopically. And this is kind of an interesting thing, right? So there's almost infinite number of options in terms of how you can set up elements and relations thereof to each other, and the rules are arbitrary, etc. And plus, even with solid elements and rules, you have unpredictable results. So it's kind of sus. So Wolfram himself is optimistic about this. He focuses on the richness of this approach. He says, well, we can do anything we want pretty much with this simplistic approach. And yeah, sure, we can, like, possibilities are numerous, let's put it simply. And he even made claims that with some of them, he was able to reproduce some of the results, not saying that all, maybe even all, of quantum mechanics and relativity, etc. But my feeling is a little bit of suspicion here. So I have a feeling that he's a little bit lost, that he may be overly optimistic. Like, I remember clearly this phrase that I've seen in one of the reviews of one of his latest books, actually the latest book about the second law of thermodynamics, in which I'm heavily interested actually at the moment. Not the book, but the law, but the book as well. However, the review made me a little bit skeptical about the book. So the review has the words self-congratulatory. Like, Wolfram is like, for most of the book, he talks about his own theory, and it's full of self-congratulatory statements. So it made me doubt a little bit in this respect. So it kind of reinforces my point that Wolfram may be too optimistic about his thing. However, I have to recognize that the potential is there, you know, the potential of his approach. And remember, we have the correspondence principle formulated by Bohr in 1920, which means that, you know, like the new theory. So we have the old theory. Again, if we're like focusing on this inside-out approach, right, top-down or bottom-up rather approach. So we have a working theory, and we're trying to generalize it. So the more general theory have to correspond to an earlier, more special theory, right? In some special cases where some other parameters are nullified or infinite, vice versa, right? So in this sense, Newtonian mechanics is the same as special relativity mechanics when the speed of light is infinite, for example. So this is a correspondence principle. So it gives us a hint, right, in terms of Wolfram's approach, where we should look for our most general theory, because it has to include these theories that we already know. So at the very least, we cannot miss any one of them, right? We have to expand it, like stretch it out a little bit to include everything we already know, in thick air quotes, actually. So yeah, so it's not actually infinite amount of possibilities, even though, I mean, strictly mathematically, it could be infinite, but the volume is finite, at least. That's kind of what I'm saying. Anyways, and plus, what I like about Wolfram's approach is that he shows the scaffolding, so to speak. He doesn't give you he's not a propagandist, you know. He has the idea, which is an approach, essentially, and he offers us to follow this approach. Not this particular path to this particular point, but rather this sort of rules, and then what kind of path are we taking? I don't know yet. Let's just figure it out, you know. Like, it's, again, remember my video about Theseus and Ulysses, two different approaches, right? So Ulysses knows where he wants to get, and he tries to drag you there. Whereas Theseus knows the rules, and he just follows the rules, and he doesn't know where he's gonna get. So he follows the, you know, the thread of Ariadne, right? So that's kind of the difference. Or my more recent video, which is only available at Patreon, at least right now, the Patreon short, psycho versus legit researcher, right? So a psycho is a propagandist. He knows where he wants you to be at intellectually, whereas legit researcher says, I actually don't know. I have a method and I follow it, and this is what I get as a result, right? And you can repeat it infinitely many times. All right. Wolfram has a bunch of young people following him, which is a good thing. Plus, he has some resources, like financial resources, like he has a company, Wolfram Research, which is kind of, again, consistent with his theory in the first place. Like, again, we have a set of rules, we have a set of resources, perhaps, and we're just following the path we're kind of like axiomatically set up, right? So we're studying this kind of thing. We don't know what we will get as the result. So again, it sounds like a legit researcher to me, to be honest. Not a propagandist at all. Like, we have some limitations by correspondence principle, but they're not absolute, right? We don't have a golden, whatever, how do you call it, golden Taurus, whatever. Like, we're not trying to get anywhere. We're just trying to figure it out somehow. It kind of makes sense for me. So we have a procedure, and let's just look what does it produce, in fact. Alright? And I have to, like, personally, on a personal note, I have to say that I've been a user of Wolfram Mathematica since 2009 or something, so almost 15 years basically, and it's been an incredibly handy tool, very flexible, very useful in all senses of the word. So in some of my videos, like about solar flares, I'll probably link it in the description, you can see Wolfram Mathematica notebooks opened where I show what I did, etc., etc. So yeah, not sponsored, by the way, but I definitely recommend anyone, actually anyone, like any intellectual, to learn Wolfram Mathematical language, because it allows you to do pretty much anything from programming to working with graphics, solving linear algebra, differential, integral equations, like you name it. I mean, it's just insanely powerful. So it's just like a, 100 years ago I would use pen and paper, but now I use Wolfram notebooks. Like, it's just the same thing, but like orders of magnitude more powerful, because you can do all kinds of things there. Yeah. So today I was thinking about recording a video about flares again, because I have some more things to say about it. But since it's Wolfram's birthday, actually, August 29th, when I'm recording it, whenever you're watching it, 2023, by the way. So he's 64 years old. So yeah, pretty young actually for a researcher. So hopefully, like, I'm very optimistic about his approach. And I think it's like, just by virtue of being so different from all the theory of everything kinds of approaches, like, it could be much more fruitful, because it's, again, sort of a, qualitative, there's a qualitative difference, right? So let's get into conclusions here. So, again, what is the difference, the qualitative difference of Wolfram's approach with respect to regular theory of everything kind of approach? Well, he gets it, he approaches the theory of everything top down, or rather outside in, you might say, whereas usually you have the set of accomplished theories, or accomplished in air quotes, and you're trying to generalize them or unite them or both, right? And you're trying to get inside out, right? From bottom up, right? You're trying to inflate them. to find the most general theory. Whereas Wolfram tries to just say, well, what kind of theory can we even produce? And then search for the more general theory inside of it. Again, looking at these beacons of already accomplished theories. And I think it's, well, again, it's original, it's very good. And I don't know anyone else, literally anyone else, who would do anything even remotely similar to that. Okay, but there's a second point in my conclusions, is this problem of computation, where it says that, well, this computational irreducibility, right, which Wolfram considers to be a feature of his theory, whereas I think it's kind of more of a bug, you know. So it's kind of, you know, personally, I feel like it's a hammer-nail type of situation. Like if you hold a hammer, everything looks like a nail. So Wolfram is big into these computational languages. Like again, he produced the mathematical language, which I used, etc., etc. So he thinks everything might be a computation. Again, see my video about the universe as a simulation, etc., etc. Even though he didn't make this statement, which I respect him greatly for, to be honest. But anyways, I believe he actually tried to force into his theory this idea that maybe we have to compute everything. And that's where actually, like, you know, emotionally, computational irreducibility comes from. Even though, as I've shown, like, you can actually logically arrive to it, right? But maybe you can logically arrive to something else. I don't know. Like, I'm just stating you the Wolfram's theory, right? It's just our observation that some systems, at least some systems, behave unpredictably, even though they're intrinsically, like, completely deterministic, right? So yeah, this requires us, if we're looking for the most general theory, for it to include these cases, which means that the theory itself should have it as its intrinsic property, right? This irreducibility. Anyways, one other problem with this theory or paradigm, you might say, is the fact that we sacrifice ontology. So we're not starting from actual actors, you know, the first, you know, the Zeus, the electron, the electromagnetic field. We don't have that. We have some anonymous blocks of whateverness, you know. So this is also kind of problematic, classically speaking, for both philosophers and philosophers, arguably, and scientists, right? So yeah, but like if you try to sum it up, it's like Wolfram's approach is procedural, right? In the end, like practically. We have the blocks that do something and something third emerges, right? Whereas in regular theoretical physics and philosophy, we have notional or conceptual approach, right? Wolfram procedural, classic is conceptual or notional. So we have these big concepts which are approximations. In Wolfram, we try to break it down completely. So there's no approximations because we have irreducibility principle, right? So yeah. Yeah. So PS, hopefully this video has allowed you to understand a little bit more about Wolfram's approach to theoretical physics, which again, I think holds a lot of potential and is unique in the sense I've described above, because it goes outside in rather than inside out, as usual approaches to theory of everything. And again, maybe you've encountered two unknowns here. That's Wolfram's theory and my own view, which I've reinterpreted Wolfram's theory from. But sometimes, you know, paradoxically, two unknowns become known together, even though you don't know any of them. Like Hilbert in mathematics have defined, he proposed this idea of implicit definition, right? So we can actually define several concepts together, right? For example, you can draw a line through 2 points. This would be a definition for both a point and a line. And try to, if you want to really break your brain and come back to me crying, try to define a point in mathematics and try to define a line in mathematics. And then again, come back to me crying. Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.